come down. Oops, sorry. X, Y. Okay, so 4xy plus natural log of x squared y equals 7. We're asked to find the derivative, dy dx. Now we know there's implicit because anytime you see y, your y variable is out of place, there's more than one y, or y is raised to a degree, or it's mixed into the equation, you know there's implicit. So we can, look at an equation and kind of tell that there's a certain look to these implicit differentiation problems. So this is implicit involved. So again, to remind us, the process for implicit differentiation is that when we come across our y variable, we're just going to find the derivative like we normally would, treat it like x initially. But then after we find the derivative for that y variable, then we need to multiply and attach dy dx. So there's implicit here. But what else do you see that needs to happen here? Good. Product rule. Product rule for the 4xy. And there's one thing, the reason that we're bringing this up in this section is because we have that natural log of x squared y. What can we do with this before we move into our derivative process? We would prefer not to jump into the derivative at this stage, because then it's going to be a pretty messy u prime over u. So what can we do with that natural log of x squared y? Is there a property that we can use? Product property, right? Natural log of a times b is equal to natural log of a plus natural log of b. We talked about how anytime you see a natural log expression, you always want to consider, is there any algebraic steps that I can do so that my derivative process can be easier? And so the process is that, well, we can split this up into multiple parts. That way the derivative can be a little bit easier to manage. So actually, before we begin our derivative here, we're going to split up that natural log of x squared y. So I'm going to just rewrite 4xy. I'm not doing the derivative just yet. So how can I use log properties to expand that? What would that look like? Yep, natural log of x squared plus ln of y. All right, there's actually one more thing that we can do expansion-wise. Yeah, we can bring that 2 down. It's not a big deal. I mean, if we didn't do that, the derivative wouldn't be too difficult. So that's not a major need. Oops. Yeah. Okay, so now we just have to evaluate the derivative for each of our terms. We know that 4xy is going to need that product rule process. And also, when we find the derivative, how many dy dx's do we expect to show up? 2, because we see two y variables. We're expecting 2 dy dx. Okay. All right, so we set product rule. All right, f prime g plus f g prime. 4x becomes 4. G function. Back to f. Yeah, good. G prime. 1. Good. So we're asking for y's derivative. This is where a dy dx is going to show up. Plus. What's 2 ln x's derivative? Yeah, so if you remember yesterday, our derivative rule for natural log of u is u prime over u, right? Okay, so 2 natural log of x becomes what? 2 over x, 2 times 1 over x, or 2 over x. Okay, natural log of y. So pretend like you're looking at an x, just find the derivative of that first. What's natural log of y's derivative? 1 over y. Yep, so now we found the derivative, attach dy dx. Equals 0. Good, derivative constant goes 0. All right, so now we're done with our calculus step. Our next stage is just trying to clean up, and they eventually want to isolate dy dx. Right. So I want to keep all my dy dx terms on the same side, and then my non-dy dx terms add or subtract to move it to the other side. So I'm going to keep my dy dx on the left. All right, now that our dy dx terms are together, what can we do? Factor, yeah. If there are other factors, we don't care about them. We only care about pulling the dy dx out. Okay, final step. Yeah, divide that parentheses over. Yeah. Okay, our derivative looks messy, but we don't have to worry about cleaning up the complex fraction. Okay. We'll come across some more review problems that involve these steps. But for now, let's go to page 5. Okay, we're going to talk about log differentiation. We're going to skip the warm-up problem at the top and move into this process called log differentiation. So log differentiation is where we take an equation, a function, a problem that has no logs in it, and we introduce logs into the problem. Now, why would we want to do that? The idea is that if we take something and introduce logs into the problem, then we have all these log properties available to us, which allows us to expand and split up problems into individual parts. If you look at example 1 here, if we want to find the derivative as is, we could. We have to go through quotient rule and chain rule. It's a lot, but it's possible. So the idea is that, well, if a problem says use log differentiation, if we introduce logs into this equation, we can break this up into individual parts. Our derivative is easier to find. Our derivative looks a little messier, but the process is easier because you're just doing individual smaller problems rather than one large problem. Okay, so here are the steps. We're going to take the natural log of both sides to allow for that balance of both sides of the equation. Next up, we're going to take advantage of log properties and expand that right side, that messy right side. There's a little bit of implicit involved because the y is no longer by itself. It's natural log of y, so we have to do a little bit of implicit. And then finally, we want to solve for dy dx, but then try to get everything back in terms of x. So here's number 1. So instruction is find the derivative using log differentiation. So first step, take the natural log of both sides, force the equation to turn into a natural log problem. Okay, so now that we're inside log problem, what property can we use to quotient property? Yep. So let's expand them into natural log of the top minus natural log of the bottom. We can further clean up, right? What can we do with this term?
You can put 1/2.
You can do 1/2.
Right.
It's okay if we bleed into example 4. We're not going to use that space. We're just going to do 1 and 2 on this page. All right. What else? Bring the exponents down. That will make our u value a little easier when we get to the derivative rule. Okay, every term, we just need u prime over u for every derivative. Let's start with the left side here. What's the derivative of natural log of y? 1 over y, dy dx. Yeah, there's my implicit. U prime over u. 2 stays. Natural log of x minus 2 becomes 1 over minus 2. 1/2, coefficient stays. U prime over u. Do a little bit of cleanup here, but essentially, I mean, this is fine. Now we have one more step here. We would like to isolate dy dx. So what can we move? Yeah, how would you move that? Multiply by what? By reciprocal, right? So I'll distribute everything through with y. I'll put the y out in front, and I'm just going to do a little bit of cleanup. Sorry, 2 minus x minus 2. I'm just doing a little bit of cleanup here. I just combined it to be a fraction. I've canceled out the 2's. All right. Now we started our function with just in terms of x on the right side, which means our derivative only needs in terms of x on the right side. What can I replace y with? What's equivalent to y?
The
original, yeah. So let's just make that final substitution. Your answer will look a little messy because we've kind of we sprawled out our equation. So our derivative will look messy, but it's okay. You can leave your answer in this messiness. There's no need to worry about trying to clean up. All right, example 2. Find the derivative of y equals x2, the 2x plus 3. Now, this is also going to be log differentiation, but the difference between 1 and 2 is that example 1, there's an option. You can, if you wanted to find the derivative another way, you could. This is just a way of an alternate way that can help us avoid messier derivative rules. But this is in the form of a variable expression raised to a variable exponent. And the issue is that we don't have a rule that can handle a variable raised to a variable. I mean, we can do a variable raised to a constant, right? X to the fifth. And then down the road, we're going to have exponential functions, which is a constant raised to a variable. There's also a derivative that exists for either form. A variable raised to a constant, or a constant raised to a variable. This is exponential function. This is like a polynomial. These we have rules for, but we don't have a rule for a variable raised to a variable. So the idea is that if we turn this into a log problem, then we can get that right side to be in a different form using log properties, and then we all of a sudden have additional rules that are available to us that in this form that we don't. So let me write the equation here. So we're also going to use log differentiation. So if you see a problem like this, you have to use log differentiation since we don't have a rule that can handle x to the 2x plus 3. And we can't adapt the power rule for this and say, okay, bring the exponent down, subtract 1 from the exponent. It doesn't work if that exponent is a variable. So let's start off introducing natural log to both sides of the equation. Okay, so now that we're inside a log expression, what does that allow us to do on the right side? Bring down that exponent, right? Okay, no derivative yet. We're just applying our log property. So now that our exponent is down, we no longer have a variable raised to a variable, which was problematic before. But if we want to find the derivative here, obviously implicit, just like before. But what do we need to do on the right side? Yeah, we could distribute, but we still are left with having to go through what rule here? What do you notice? If it helps if I do that, what's involved? Variable expression times a variable expression. I got to go through what? You guys remember? Product rule. Yep, we got to do a product rule. Now, if you see a problem like this, a variable raised to a variable, we're always going to end up with product rule, because what's going to happen is that variable is going to come down, so it's going to turn into a variable times a variable expression times variable expression, and unless they can merge together, we have to go through the product rule. So you can expect product rule to show up for any problem that's in this form of variable raised to a variable. Okay, so natural log of y, just like before, same process, 1 over y, dy dx. Okay, f prime, 2x plus 3 becomes 2. G function, no changes. Okay, back to f. And then G prime. Okay, final step. What needs to move? Multiply both sides by what? Y, yeah, force that Y to come over to the right side. Okay, final step. Let's get everything in terms of X. So what can I replace that Y with? Yeah, the original equation.
What do you get 2x plus 3 over 2? Oh, yeah.
Oh, sorry, 2 plus 3 over X, my bad. That's fine. Copy it.
You cancel out the extra now and make it 2 plus 3.
Well, you could split up into individual fractions and make it 2x over X plus 3 over X and reduce.
Okay.
But if you leave unsimplified, I'm okay with that. Okay, we have one more new topic today, and that is derivative of inverse at a point. So let's go to page 6. Let me just review a little bit with inverse functions. Inverse functions is where you take a function or take an expression, and then you create another one by swapping the x's and y. So wherever you see an x, replace with a y. Wherever you see a y, replace with an x. After that, you know that a function and its inverse will always be symmetrical over the line y equals x. So just for instance, if a graph looked like this, if one graph looked like this, the inverse function will look like as if you were folding this graph over the line y equals x. If two functions are inverses of each other, then if I were to plug one into the other function, all I'm going to get is x. So they're going to cancel out to be x, which makes sense because if I were to divide, or if I were to plug one into the other, when they cancel each other out, what's left is this y equals x line, which is that dotted line that's diagonal line cutting across your graph. Let's do a quick example of inverses. So if I have a function y equals 6x plus 2, okay, if I want to find the inverse, I'm going to swap the x and y and solve for my new y. So subtract x from both sides, subtract 2 from both sides. If I solve for my new y, I can divide both sides by 6. This will be my inverse function. So if I were to plug this into the x of the original function, they're going to cancel out, and now all I'm going to get left is x. If I were to take this 6x plus y, put it in for this x, everything will cancel out except for x. Okay, we're going to use this space here for me to I want to draw a diagram for us to help us visualize what we're after here. We're trying to find the derivative of the inverse at a point, but for the most part, we're not going to be using the inverse function. We're going to use the inverse property from the original function. So let me just demonstrate something with the graph here. So I want you to draw a graph. Dotted line to indicate where the graphs will mirror each other. Let's say we had a graph that looked like this. Let's call this graph f of x. Let's say there's a point that lives on this graph. And let's say that point is 1, 4. Let's create an inverse function. Just try to make it so that it's a mirror image of this graph folded along this dotted line. And let's call this the inverse function. So a function and its inverse will always have flip-flop order pairs. So if there's an order pair 1, 4 that lives on the function, there's going to be what order pair that lives on the inverse function. No, not 1 more. 4, 1. Yeah. So if I have order pair 1, 4, then there must be an order pair that is 4, 1. Right? The idea that in between the function and its inverse, if my x's and y's are flip-flopped, are swapped, then that means if I change that order, that point will sit on the inverse function. Okay, so that's one property that that we know of between order pairs. Okay, so any order pair that lives on one graph, I can flip the order of those values, and that new order pair will live on the other function. Okay, so that's just the property between the function and its inverse. Now there's a new property that I want to talk about, and that is from the derivative perspective, the slope perspective. There's actually going to be a relationship, a numerical relationship between the slope at this point versus the slope at this point. I want to see if you can guess it. Let's say the slope of this graph was at 1 was 1/7. Sorry, it's 7. Right? Steepness of 7, pretty steep slope. If you had to guess, what's the slope of this? Yeah, it'll be the same numerical value. You're just going to take the reciprocal. So what I can say here is f prime of 1 is equal to 7. However, the derivative of f inverse of 4 is equal to 1/7. Notice that these are corresponding points. The x value for the function is not the same x value for the inverse. But at their corresponding points, we're going to get that reciprocal slope. Yeah, so basically f inverse, the derivative of f inverse at 4 is equal to 1/7. But the derivative f derivative at 1 is equal to 7. So I just want to point out that these corresponding points, they're not going to be at this, these will not be the same numbers. But they're going to be corresponding to each other because they're related in the sense that they're both involved in their individual order pairs. Yeah. So basically the x for one would be the y for the other. So there's a certain relationship that I'm going to have us use to help us move our way through the problem. What we're going to do is the first row, I want us to establish that relationship between the function and its inverse, that their order pair will be flip-flops. So there's order pair A comma B that lives on the inverse. There's order pair B comma A that lives on the function. And if at their corresponding points, their slopes will be reciprocal to each other. So example 6, f of x equals x cubed, sorry, that's x cubed plus 4x plus 2. Find the derivative of f inverse at -3. So we're always going to be looking for this bottom corner of our table. And we're basically just going to work our way around the chart. And by the time we work our way around, we're going to have enough data to get to our answer. So this is the way I like to start out. Create your chart and put what you're trying to look for in the bottom corner here. So -3 is the x value of my inverse function, right? So I'm going to put my information about my order pair of my inverse function above. This is asking for the slope. This is asking for the order pair. Now, if -3 is the x value of my inverse, then -3 must be the what of my function? Y value. So this is what I have. I have the function given to me. I don't know what the x value is, but I do know that if I'm building a corresponding relationship, -3 is the x value of my inverse. It must be the y value of my function. Are we okay with that relationship? Okay. So now we have to do a little bit of piecing together here. We want to figure out what order pair is going to allow me to move into my relationship here. -3 is not the x value of my function. -3 is the y value of the function. What's given to me is the function. And you're always going to be given your function expression. You're never going to be given what your inverse is. So I know -3 is the y value. So I'm just going to work on this equation and see if I can work backwards and figure out what is the x value at this point. Okay, so -3 is the y value. I'm just working backwards to figure out what the x value is. I'm going to bring everything over to one side. And what you're going to notice is that if we try to solve for x, it's not going to be factorable. Okay? So if it's not factorable, we're going to try to guess and check our way to get the answer. But the good news is that it's going to be a number easy to find. It's going to be a number close to 0. So if it's not 0, then there'll be 1. If it's not 1, then it's -1. So after a few tries, just test numbers around 0. Eventually, you're going to get that number. Okay? Because if it's a guess and check thing, it's going to be easy to find. So let's do 0 first. 0 is the easiest number to plug in. Is 0 going to work for this equation? No. Okay. What about 1?
No.
1 is not going to work. What about -1? Okay, so -1 for x, -1 for x here. So -1 minus 4 is -5. -5 plus 5 is 0. So x is -1. So let's go ahead and build that relationship here. If there's an order pair -1, -3 on the function, there must be an order pair what on the inverse? -3, -1. Yeah. So this is just to establish that flip-flop relationship between the function and its inverse. Okay, so if I can find the slope of my f graph at -1, and I can do that because I have a function for me to work on, then this slope is going to be related to the slope that I'm ultimately looking for. Even though I don't have anything on this side, we're using this function and build that relationship from the other side. So let's find f prime, and then we can find the slope of f prime at -1. So what's f prime of x? Three x squared plus 4. Okay, what's the slope of my f graph at -1? 7. So if the slope of my f graph is 7, then the slope of my inverse at its corresponding point must be 7. Sorry, it's not always going to be 7 and 1/7. It's just having to choose that value here as well. So that's the process that I want you to go through here. Yours is going to build. You're going to start your unknown here, and then we're going to work your way around the chart. And by the time you move, you're all the way around. You're going to have enough data to make your final conclusion about your relationship. All right, example 7. we're trying to find the derivative of f inverse at 1, and you're always going to be looking for the derivative on the inverse side. So 1 is the x value of my inverse. I'm going to build that order pair relationship here. If 1 is the y value, sorry, if 1 is the x value of my inverse, then 1 must be the what of my function? 1 must be the what? The y value. So I'm going to say f parentheses equals 1. So whatever, basically whatever number they give you is always going to be the y value on the function. So I'm going to say 1 is equal to the square root of x cubed minus 7. I think this one we can solve by hand since it's not like multiple terms, just 2 terms here. What can I do to make my way to solve for x? Is there any way to get rid of the square root? What can I do? Yeah, raise both sides to what? Not 1/2. How do I undo a square root? Squared. Okay. I'm going to square both sides. 1 is equal to solve for x. X cubed equals what? Add 7 to both sides, 8. Okay, take the cube root of 8, 2. All right, so we've established our relationship. There's an order pair 2, 1 on the function, and there must be an order pair 1, 2 on the inverse. Okay, move down. We want to find f prime of 2. Before we can find f prime of 2, we first have to find f prime of x. To find f prime of x, we have to go through what rule? What's required if I want to find the derivative? Chain rule. Yeah. So outside times inside's derivative. 1/2 parentheses to the negative 1/2 times the inside's derivative times what? Your x squared. I'm going to bleed into example 9. Example 9 is not going to take a whole lot of space. So I'm going to clean this up here. F prime is equal to 3x squared over 2 square root of x cubed minus 7. Okay, I'm going to plug 2 in to get to my slope on the function side. So I plug 2 in for x. I get 3 times 2 squared, which is 12. 2 cubed minus 7 is 8 minus 7, which is 1. So 12 over 2. What's 12 over 2? So if the slope on my f graph is 6, then the slope on my inverse side must be what? 1 over 6. The next 2 should be easier because all the data is in front of you. We're just making our way around the chart. Okay, we want to find f prime of 2. Whatever you're looking for, start at the bottom right corner, and you're working your way around the chart. So I know 2 is the x value of my f function. Sorry, 2 is the x value of my f function, which means that 2 must be the what on my g function. Oh, and by the way, if you see that notation, that's just establishing that f and g are inverses of each other. So again, if 2 is the x value of my f of x, then 2 must be the what of my g, the y value. Okay. They're always going to have flip-flop order with their points. Is there something that is true that I can fill in for g? Okay. G of 7 equals 2. So if there's an order pair 7, 2 that lives on the G function, there must be a what on the F function? 2, 7. Right, just like over here, right? We were basically establishing that relationship between the function and its inverse. My order pairs will always be in a different order. So I'm working on my G function here. So do I know what G prime of 7 is equal to? What's that equal to? 10. So that should be enough, right? If I know G prime of 7 equals 10, then F prime of 2 must be right. Try number 9, see if you can see if that process makes sense that we did with number 8. Before we even look at the properties here, we know where that 3 is going to go, right? We know 3 will be the X value of my F. We know 3 must be the Y value of my G. So we can just always make sure, always start here. Fill in that first number into those slots. All right, is there something that is true that's going to fit into this pattern here? Yep. So there's a 9, 3 on the G. There must be a what on the F? 3, 9. If I can figure out G prime of 9, right? We're talking about the same X value on the G function. What's the slope of the G graph at 9? That's all we need because there's a numeric relationship here. F prime of 3 must be what? 1 over negative. Yep. Okay, next page. I want you to try 73 and 74. Let's go back to implicit. Just be careful with 74 here. You want to expand first, especially if there's natural log involved. So the process is find the derivative of each term. If you come across y variable, find the derivative of that. Treat it like x initially, but then attach dy dx. Right back. You still don't think I trust it?
Yeah.
You think him? Didn't you trust the captain though? Didn't you trust people like?
It's already different. That's like put out. Includes. So that. There's one in law, the sense that she kept. It's actually.
No.
But there's.
It's like empty.
Yeah.
The office is like fully. Yeah, it's so easy. That was the easy one. That was the easy one.
Which one?
The first question. The MT one?
Oh, yeah. And he's.
The
They
one,
should
everything
have
else.
to do like this, like,
Yeah.
yeah.
Yeah,
But it was like different.
Yeah, so-
Yeah, it was wonky.
It was
weird.
really weird.
It wasn't like normal. No.
Yeah.
It was hard to.
It actually was pretty fun.
Yeah.
I was like, wait, you guys did that last night for practice. You know, this were like Mason, like the ice cream shorts, like. That's a good one. If we were doing Halloween football, that's so funny. Avery and Reese's every year. Oh my gosh, it was actually miserable though, because it was so cold. Oh, like I just wanted to leave all the time. Yeah. No, I can just imagine like that just being freezing in the costumes. Like my costumes. No.
Don't know how to do football. Oh, don't worry.
You're welcome.
It's something. Yeah. Which is yeah.
Really? It's like, oh, actually.
No, I didn't. That's Joy has it. Joe, what do you get from? It's 72. Negative 2x over negative.
That's over.
That's over Washington. Basically,
What's Joe's?
I'm doing. Sorry, God. One square. Actually, oh, I forgot. I wrote the problem. It's right now, it's too much. What? It's just right. Oh, yeah. It's closer.
If you leave your answer in complex fraction, I'm okay with it, so we don't have to clean up past that point. Okay, so 73. Notice there's two y variables, so we know that there's going to be ultimately two d by dx's that's going to show up. X squared is 2x, 3 natural log of y. Natural log of y is 1 over y. Times dy dx. Y squared, power rule for y squared, 2y. All right, so whenever you see a y variable, pretend like it's x to begin with, and do whatever derivative rule that you see there, and then at the end attach dy dx. Careful, a constant is also getting impacted by your derivative rule, so 10 doesn't stay there, it goes to 0. And the rest of it is just moving things around, trying to solve for dy dx. (74) natural log of xy. We want to take advantage of log properties, so we can avoid messier rules. We would prefer not to have that xy being our u value for our natural log. So if we expand first, notice that there's only one y variable, so only one dy dx will show up in your derivative step, and then solve for dy dx.
Can you explain the derivative of y squared?
Yeah, y squared. What's the derivative of x squared? 2x. What's the derivative of y squared? 2y. So as soon as you find the derivative, whatever that process is, attach dy dx because there's y's involved.
Yeah. The second, how do you solve this?
Yes, question. This is fine. We could go a little further and clean up, but I'll accept that anyway. Yeah.
Oh, yeah, we can bring it more. Well.
Any other questions?
Only get done by time.
What?
One sequel theory.
Natural log symbol, when you take the derivative of y does it, what is it?
Well, it's never natural log itself. It's always natural log of something. So we always have that something there. You're never going to see just natural log by itself.
Right.
So that natural log of x, the derivative is just going to be 1 over x. Yeah. So when you find the derivative of this function, there's no more natural log in it. It just turns into the derivative without natural log. Yeah. So it's basically disappears anytime you find the derivative. Yeah, that's just the way that relationship works. So Monday we have one more new topic before we start reviewing for our quiz. What do you mean?
It's your car and you have one for your town. Exactly. Like, it's like then you gotta get, I can't get a loaner because I'm not 21. So like, I have to get my dad coming out and it's like my car.
Yeah.
And then.
Yeah.
You know,
Oh,